Alright, silly people, here's the situation. We have a hydrogen atom that is in an electric field that is time dependent, and we're going to be calculating the probability that the hydrogen atom starting in its ground state will excite to the first excited state um, over an infinite amount of time, right? Uh, so this is a time-independent perturbation theory problem. The probability will ultimately be given by, uh, the probability that it will go from the ground state to some uh, first excited state, so 2LM, will be given by squaring the coefficient d 2LM, um, which that coefficient is given by this equation. D sub f of t equals Kronecker delta fi minus I over h bar integral from 0 to t. Then we have the bra of the final state acting on the perturbed Hamiltonian, acting on the ket of the initial state, times the characteristic frequency omega fi t prime and integrating over t prime, right? So given that we know that the hydrogen atom is in the ground state, I already kind of wrote it, but we know that this I0 ket is just the 1, 0, 0 ket for the hydrogen atom. We know that we can find that the perturbed Hamiltonian is just the electron charge times the magnitude of the electric field. And the fact that we are given it that it's in the z hat direction, well, we know that it will have a linear dependence on z. So there's that. And we can actually write out now what the Shankar gave us for the electric field. The electric field has this expression, fancy E times e to the minus t squared over tau squared, z hat, right? So then the perturbed Hamiltonian is just e fancy e to the minus t squared over tau squared z. The only operator in there is z, so that when we write this big equation that we've been looking at, the only thing that's going to remain in the matrix element is the z. And I think with that, we are ready to write this. Oh, no. We also need to point out that since we're looking at the probability that it could go to any n equals 2 state, right now, for now, this is the 2LM ket for the hydrogen atom. Now we can write this big old equation. So we can write the df of t now. It's going to be d, I'm going to move it down a little bit, d2, oh my god, d2lm of t. The Kronecker delta will go to 0. We're not including the probability that it'll stay the same. So this is now just minus I over h bar. We can pull out the electron charge E and also the fancy E. And we can even pull out the matrix element, because the only thing that is going to be left in that matrix element is the z operator. So I'll just pull that out. It'll be 2LM. It'll be Z100. And then the time-dependent stuff just ends up being e to the minus t minus t prime squared over tau squared times e to the minus I omega t prime dt prime. And it's not actually little t for the function bound, it's infinity. That's because we're letting it go for an infinite amount of time. And for the lower bound, we'll change 0 to minus infinity because it makes the math nicer. Right, so this time integral, actually, Shankar already did, and I'll write the results that he got before we really discuss anything else. So we got minus I e fancy e over h bar. The result of that integral is e to the minus omega squared tau squared over 4 times the square root of pi tau squared, right? And then because of selection effects, the only non-zero matrix element here is actually 2, 1, 0, z, 1, 0, 0. And we're going to have a time figuring out what that matrix element actually is. We're going to do it in the old-fashioned way, Griffith style. Well, by definition, this is the integral over all space, so d3r in 3 dimensions, of the wave function conjugate to 1, 0, and then multiplied by psi 1, 0, 0. Where those wave functions are defined for the hydrogen atom like this: psi NLM RNL of R, that's the radial component, and then a spherical harmonic YLM LM of theta and phi. So we can use this to get the forms for the wave functions. I already did, and so I'm just going to copy down what those are looking like. So I got these definitions from Griffiths, by the way. R21 is 1 over 2 root 6 a naught to the minus 3 halves r over a naught times e to the minus r over 2 a naught times 1 half root 3 over pi cosine theta. All of this stuff was the y 1, 0 spherical harmonic, right? And you can simplify that. Root 6 has root 3 in it, so I'm just going to write it as r over 4 square root 2 pi 1 over a naught to the 5 halves e to the minus 2, no, e to the minus r over 2 a naught times cosine theta. And we'll leave it like that for now. We'll do also psi 1, 0, 0 given by r 1, 0, which is just 2 a naught minus 3 halves e to the minus r over a naught, and then the y 0, 0 spherical harmonic, which is just 1 half square root of 1 over pi. This can also be simplified, but not too much. It's just e to the minus r over a naught over a naught to the 3 halves times root pi. So then the big matrix element 2, 1, 0, z 1, 0, 0 is now looking like well, it's an integral uh, of solid angles, and then an integral from 0 to infinity dr of, yeah, this is a lot of junk, isn't it? Let's just write it all out. R over 4 root 2 pi 1 over a naught 5 halves e to the minus r over 2a naught cosine theta. Z in spherical coordinates is just r cosine theta. And then psi 1, 0, 0 here we'll have e to the minus r over a naught over a naught to the 3 halves root pi. Right? Wrong! I actually forgot to write r squared at the front there, so just be careful of that. You should have an overall factor of r to the 4th in your integral. Simplifying a bit and also starting to split up the integrals, we'll have 1 over 4 pi root 2 a naught to the 4th down here. And then we'll have an integral over d phi, as well as an integral over sine theta cos squared theta d theta, and then our integral 0 to infinity dr r to the 4th e to the minus 3 r over 2a naught. The radial integral, I'm going to do a u substitution. I'm going to say u is equal to 3 r over 2a naught, and du then is 3 over 2a naught dr. I'm going to actually do the azimuthal integral because it is just 2 pi, so that isn't hard, I don't think. I'm going to expand this integral using the trig identity where cosine squared theta is equal to 1 minus sine squared theta. So we have just an integral of sine theta d theta, as well as minus the integral of sine cubed theta d theta from 0 to 0 to pi. Blech. And then the radial integral, now that we've factored out the u stuff, we'll have 2a naught over 3 to the 5th to account for r to the 4th and dr. And then in here it's just the integral from 0 to, or minus infinity to infinity. No, it's 0 to infinity of u to the 4th e to the minus u du. Okay. Simplifying again, I see that we have, come on, see we have pi's here that will cancel out. This 2 will turn into 2 on the bottom here, but then there's also 2 to the 5th over there. I think that's enough simplification for now, actually. So we'll have 1 over 2 root 2. I'm actually going to not write 1. I'm going to write 2 to the 5th a naught to the 5th. Down here we'll have 3 to the 5th and a naught to the 4th. Right. Then the rotational integral, I mean the theta integral, whatever, that's cosine theta, that's a third cosine theta times sine squared theta plus 2, which we have to evaluate at the bounds. And then the u integral just turns into the gamma function of 5. Continuing to simplify, I see we have a 2 on the bottom, so this is going to turn just 2 to the 4th, a naught to the 5th, with a 3 root 2, 3 to the 5th root 2, and actually just 1 power of a naught up top because it'll cancel out the 4 on the bottom. And then cosine theta of pi, so minus cosine of pi is 1, cosine of 0 is 1, so plus 1, plus 1/3 times, actually no, it's not plus 1/3, it's minus 2/3, and then minus 2/3 again for theta equals 0. And then the gamma function of 5 is just 4 factorial. Continuing to simplify, 4 factorial is 4 times 3 times 2. So 2 squared times 3 times 2. So we'll actually just have 2 to the 7 up here now, and 3 to the 4th down here, and a root 2. And then this is just 2/3 in there. So actually we'll have 2 to the 8th a naught over 3 to the 5 root 2. That's it. So we can go back to our constant d210 of infinity is now looking like minus e fancy e over h bar root pi tau e to the minus omega squared tau squared over 4 times 2 to the 8th a naught over 3 to the 5th root 2. And so the probability then that will go from the ground state into this excited state will be given by that constant squared, which will be e squared, fancy e squared, over h bar squared, pi, tau squared, e to the minus omega squared, tau squared, over 2. Then we'll have 2 to the 16 a naught squared over 3 to the 10 times 2. And it's necessary to simplify that by one more thing. That e was too fancy. Fancy e, h bar squared, pi tau squared, to the minus omega squared, tau squared over 2. And then this is 2 to the 15 a naught squared over 3 to the 10. Yeah. And that is looking like what Shankar got, so we are good there. Awesome.